Hello, in this video, we will be seeing how to find a target element in a rotated sorted array and build a solution in JavaScript while also computing the time complexity and space complexity of the solution. For the problem statement, we will be given an input array that has been initially sorted and then rotated by a pivot index which is unknown to us. And we are given a target which we have to then find in this rotated array. We will be building a solution using binary search because the original array was sorted, but we have to tweak it a bit because after the sorting we had performed a rotation. And we will first begin with the original approach for binary search and tweak it as we go along. And let's take an example here wherein we want to find a target of 0 in the input array nums that we have received. And we will start with a left pointer to begin with, which is going to be at index of 0, and we are going to have a right pointer which is going to be at an index of 6. We will then find a midpoint which is going to be 0 plus 6 by 2, which is giving us 3, and the midpoint is going to exist here because this has an index of 3. Then what we said, in normal binary search we will just compare this value that we have found at midpoint with a target. In this case they are not matching. Then we will see in the left subarray, we have to see inside the left subarray whether the target exists or not as per the bounds of the left subarray if it is sorted. How will we know that the left subarray is sorted or not, or any array as a matter of fact in this matter? Because we have a left array here, so one left array after we split based on the midpoint is going to be this, and another subarray that we are going to have on the right side is going to be this. Now within these two arrays that we have with us, at least one will be a sorted array because we have first sorted the input that we have received, then this sorted input is rotated. So if you split at the midpoint, at least one from these two will be a sorted array because of the design of the process before you split it. And in the best case, both sides can be sorted arrays. And to know whether an array is sorted or not, we can pick up the left bound here and see if the lowest element that you have, which is pointed by the left pointer, which in this case is 4, is less than or equal to the upper bound, which is this 7. So we have two parts, one is the left subarray and one is the right subarray. And if the left value that you have is less than or equal to the upper bound, which is 7, then you can say this is a sorted array. So this is step 1. Step 2 is, after that we have to make sure that our target, which is 0, falls within the bounds of this left sorted array. So you know now that the array is sorted because this check passed. Then for this sorted array, I have to make sure my target is within the bounds, which is checked by making sure that the target, which is my 0, has to be greater than or equal to my lower bound that you have. So I will say 0 has to be greater than equal to 0 is greater than equal to my 4, which is not the case. So I will not consider it. The second bound I have to also check is that my 0 has to be less than my 7, which is true in this case, but the first check that target falls within this bounds is not being met. And why do I have to put this check is because we are working here with a rotated array. In the original binary search, whenever you found midpoint, and if you have gone down to the left subarray because the value was lower, we were completely discarding the right subarray and moving on with the halved array. But in this case we don't do that. We consider the left side to be a sorted array. If it is sorted array, then we do a check to make sure target falls within this bounds because it's a rotated variant. Then if it is falling, then all good. You keep your bounds on the left side and work with them so that the right bound will then move here. But in this case what's happening is my target, which is 0, is not satisfying the condition of bounds, so my answer is not in the left subarray, my answer is in the right subarray. So I will then move on to my right subarray by shifting this left value that I have itself on the right subarray, which is going to be mid plus 1, and that mid plus 1 is going to come here, and this is my new left, which is at 4, and I will only work with this right subarray to try to find my target. If I don't find, I will just return -1. Then from this I will go on to my second iteration that I have a left at 4, I have a right at 6, by 2 is going to give me 5. So this is going to be my new mid now that I have. With this new mid value that I have, I will check whether this is a target. It is not the target. I will do the check for the sorted left subarray, which will fall within this bounds that I have highlighted here. Then I will make sure my value on the left side here, which is going to be 0, has to be less than or equal to 1, which in this case is true. So it is a sorted left subarray. I will then move further inside, and then I will check whether my bounds are being satisfied by the value that I have. My 0 that I have with me, which is being the target, has to be greater than or equal to my left bound, which is true, plus my 0 has to be less than the mid value that I have, which is 1. In this case, both are satisfied. That means it falls within this bounds, and then I have to move forward with my index that I have. So my left condition is set, saying that the value exists in the left subarray, and because of that, the right pointer that I had with me now will be now shifted for mid -1. Mid is at position 5, 5 minus 1 is 4, so it is going to get shifted at 4 now. So this is pointing to my left and right pointer. I move on to my third iteration that I have. I will see 4 plus 5 by 2. It is going to give me this value here that I have, which is going to be 4. And at this index now, I will check whether the value I have is my target. It is my target, so my output is going to be 4, which is the index of the target that I'm looking for. And that's pretty much it in terms of implementation. Now, the key aspect here is that we did a variation wherein in the original version, if the value did not exist on the right part with the target being lower than the midpoint, we were just skipping the right side. But in this case, we are not completely ruling out the possibility of the target being on the right side because of the rotation. So first we see find the sorted left subarray or the sorted right subarray, and within then I check whether it's within the bounds. If it's not with the bounds, that means it's in the other array that is existing. And that's pretty much it. Now let's jump into the coding aspect of it. So first we said that we will be using 2 pointers, the left pointer and the right pointer. The left pointer is going to be at 0 and the right pointer is going to be at the end of the array that you have received. So left is 0 and the right value that I have is going to be nums.length -1. That is the upper bound of the input that we have received. Then I will say while my left is less than or equal to my right, which is the criteria to keep moving forward in a binary search, I will do the logic of finding the midpoint, and at the end, if I am not able to find the midpoint, I'm just returning -1. Then within this while loop, I will say midpoint is equal to something. That something is left plus right by 2. But I can represent it in a more robust manner by doing something like this. mat.floor left plus right index minus the left index by 2. This is to make sure that even for lower level languages, it gets handled smoothly and it is more robust in comparison to just doing left plus right by 2. And then what we will do is, if this nums of my midpoint is equal to my target, that would mean that I have found my target which I was looking for, and I will just return my mid index because mid is the index that we are tracking, and the aim here is to return the index as an output. Then if this is not the case, then we make sure that we try to see at least one subarray that is sorted is found. First we will see if the left subarray is a sorted array or not, and to do that check we will just say nums of left is less than or equal to nums of mid. If this condition is met, then it means that the left subarray is sorted. Otherwise, because we know that at least one subarray is sorted, we will then check for the right subarray. Now within the left subarray, once we make sure it is sorted, we have to check the target falls within the bounds of the subarray. So target has to be greater than equal to nums of left, and target also has to be less than nums of mid. These are the bounds of my left subarray, and if this condition is being satisfied, that means the answer lies in my left subarray itself, and in that case the right has to shift now to the point before the mid value. So in that case I will just say right is equal to mid minus 1. But if that is not happening, that would mean that the answer, which is the target, is not in my left subarray, and I have to start looking in the right subarray, which I would have not done in a regular binary search operation because I just discarded the right half if it is the original implementation. But in this case I don't discard it. So then I will say my left is going to be otherwise the mid value plus 1, so that I shift my execution to check for target in the right subarray. And similarly for the right subarray, I do the same checks to make sure it is within the bounds. So the target has to be less than the nums of my right end that I have, which is the nums of right. So it is either less than or equal to my right side, and my target has to be greater than nums of mid. So these are the bounds of my right subarray, and if it is within these bounds, that would mean the answer lies within the right subarray. So I have to then move my left pointer that I have towards the right, that is towards mid plus 1. In that case I will just do left is equal to mid value plus 1. Otherwise, in that case, if it is not being satisfied, then what do I do? In that case, what I will just do is the opposite of this, which is basically saying right is equal to mid minus 1, and that's making sure if it is within the bounds, then you are going to start looking in the right subarray, which means basically your left is going to move now towards the right subarray. Otherwise, your right itself will move in the left subarray to start checking. That is going to be mid minus 1, and that's pretty much it in terms of the implementation that we have here. And in terms of the time complexity that is going to be involved here, what we are going to do is use binary search here, and because of that the time complexity will be big of log of n. And here, after I find this check here of doing mid is equal to target, I will just make sure that the wrapping is correctly put here, wherein I will just say if this condition is met, and I will also make sure my brackets are put correctly. That's pretty much it. Now let's compute the space complexity also of the solution. It's going to be bigger of 1 because we're just using 2 pointers here, and they are keeping on getting updated as we search through our input. And as we said, the time complexity is going to be bigger of log of n because the approach being used here is going to be of using binary search, and binary search comes with a time complexity of big of log of n. Thank you for watching. Please like and subscribe.